Well, good afternoon, everyone. I'm Paula Gearon. I work at Cisco, and this presentation is about automatically generating Datomic schemas from third-party data. In particular, this is a case study from the system that I presented at the last conj, which was Naga. It's a rule engine for graphs. For graph databases, sorry. And it's written entirely in Clojure. I presented pretty much the operation and semantics of the system last year, so if you want to have a look at it, you'll find that on the YouTube playlist for the conj last year. Now, I'm not expecting that I'm going to be presenting anything novel for anybody who's familiar with Datomic, but if you have any sort of experience, then all you're going to find is that I'm just gluing things together in slightly different ways. So when I presented my talk last year, Naga had preliminary support for Datomic, but since then, Datomic's become our graph storage of choice. So we've had a lot of extra focus now on the features and requirements of storing things in Datomic. One place where Datomic differs significantly from other graph databases like RDF stores is in the need for a schema. So a lot of the Datomic specific work was focused on that. The work was informed by other projects that I've worked on working with Datomic where we've done similar sorts of things. Initially, the Loom project, which was originally developed at Revolytics and then acquired by Teradata, and an open source project called Cast, which would parse Clojure source code and store it in Datomic. So this store is specifically about loading JSON into Datomic. That's because the data that we receive in our systems is always given to us as JSON. Naga uses the semantics of description logics, which get encoded into graph form. While that's not essential for the data, the data that we're processing to have graph semantics, it does require that the data get converted into a graph to work on it. Fortunately, the data that my group at Cisco has been working on is already in a graph shape, so Naga was a natural fit for it. However, we do receive all of our data in JSON form. That's because JSON is simple, it's portable, and it's a common standard for network communication, especially over HTTP. As Rich pointed out yesterday, it's the default format for transport, so Naga had to be able to work with that as well. To start with, we knew exactly the shape of the data we wanted to execute rules over, meaning that we knew all of the attributes we'd be getting and the associated data types. I wrote that schema by hand and loaded the schema into Datomic before trying to import the JSON for it. Then I needed to load more data types that were also represented in JSON, so I extended the schema to handle those new attributes. Then I needed to load more types of data, and I extended the schema again, all of this by hand. But I was inferring most of this from example JSON objects, and it seemed to be a very straightforward conversion. So after that first expansion, it started becoming clear that I really wanted to have a tool to automate this. Every time I did it by hand, the need for that tool increased. So eventually, I bit the bullet and wrote the code that was going to do all of this automatically, which is what I'm going to be showing here. Now, despite the talk of this, the title of this talk being about Datomic schemas, Just as much of the work is in the structural representation of the data. So if we consider what JSON looks like, we can consider how we want to represent it. This is indicative of the kind of structure that we're going to get in our JSON documents. At the top level, we've got an array of objects where the objects in this example represent people. It's possible for JSON to have an object at the root rather than an array, like I have here, but all of our systems don't do that. The one occasion I needed it, I just wrapped something in a single element array. So you'll see here that the objects have attributes of type, first name, the inner objects have a name instead, age, children. Type, first name and name are all strings, age is an integer, and children is an array of objects, and you can see that those objects are people as well. So if we avoid considering the array structure just for a moment, we can see that JSON is in a tree, and that's possibly evident from the syntax, but I pulled it out here, with the roots starting at the top of the level objects. Now, each individual object in the JSON is represented as a node in the tree, which in this case, I've given arbitrary identifiers. This lets me refer to those objects by ID, which will be important in the next slide. Because tree shape in JSON is easily represented as a directed acyclic graph, or a DAG. Each attribute relationship in a JSON tree then becomes an edge in the graph. The attributes become labels on each edge, though I'm not showing them here. Again, the objects in the original JSON require nodes in the graph, which requires unique labels so we can get to them, and we can arbitrarily assign those as well. You can see how each of these edges can be represented by a 3-tuple of entity attribute value. So Datomic is a graph database, which is exactly what Naga needs, but Datomic also has an entity API. This represents nodes in the graph as entities, with edges of the graph being attribute values for those entities. These entities look very similar to JSON objects. So, naturally, we should try to store these JSON objects as entities where possible. The idea behind this is to allow the data to fit with less manipulation. It also means that anyone who wants to access the Datomic store directly without using the Naga APIs ought to see the data that continues to make sense, and they'll be able to interact with the data using standard entity APIs. That wasn't originally the plan because we had hoped to swap different databases, but as we've come to rely on Datomic more and more, people going to look at that data tend to use the Datomic APIs. So the first step is considering how we want to encode JSON data, is to look at the types of data that JSON supports. You'll see here that the set of types isn't very large. It's strings, numbers, objects, arrays, booleans, and the special value nil. Now, many of these aren't supported in Many of these aren't supported in Datomic. Many of these are supported in Datomic with a couple of tweaks. One point worth noting is that JavaScript uses 64-bit floating point values for all numbers, but because our systems are all using Cheshire, integers or longs in closure are encoded as integers in the JSON stream and decoded that same way. So we don't normally need to deal with ambiguity there either, because Cheshire will generate floating point notation for attributes that use floating point numbers, and it'll use a 0.0 notation when that happens to correspond to an integer. But when the original data starts as an integer, it'll be encoded as one and decoded back into one. But as you can see, Datomic has a much larger set of data types available to it. So if we consider the types that JSON requires, we only need to use a few of them. You'll note that I've highlighted both long and double. Strictly speaking, JavaScript would only need the double, but because we want to be able to maintain integers, we're using both. And we can We can infer that based on the data stream we receive. Also, we're using the reference type for objects, since that's the type that is used to refer to other entities. Two things that are missing from Datomic are arrays and null types. We need to deal with those using structures in the graph instead of something simple in the schema, and I'll discuss that in a moment. So for a simple conversion, if we just look at the embedded children in the first example that I showed, we can see that we have very simple data types which are straightforward to work with. In this case, we're just looking at type, name, and age. Now those attributes refer to strings for the type and name and integers for the age. And those same attributes get used for both objects. Now, each object property gets converted into an attribute whose ident is the attribute name and whose value type is the data type for the value of that attribute. And you'll notice that we're using the cardinality of 1 for everything, and that's consistent with objects in JavaScript or JSON, since a key can only refer to a single value. We used to have an attribute definition which referred to the DB partition, and this would be shown as a reverse attribute on each of the declarations, but the need for that went away recently. But if anyone were to have a look at the Naga code, you'll find that most of our attribute definition still includes those declarations. Now, the previous slide just jumped straight in and used JSON keys as the basis for attribute keywords. Now, that worked in the example, but how reasonable is this? Most of us probably use namespaced attributes in Datomic, or we should, but Datomic does get along just fine without namespaces on keywords. Since the rest of your database should be using namespaces on attributes, then there ought not be any conflicts. However, if you're concerned about using multiple JSON documents with conflicting properties everywhere, then you may want to consider an approach that maps your document type into a namespace and incorporate that into the attributes being scanned appropriately. A more important issue is that JSON strings don't follow the same rules as keywords. For instance, an attribute on a JSON object can include a space. Now that's not legal closure syntax, so what are we going to do in that case? One approach might be to just convert those labels into camel case or replace spaces with dashes, but that runs a minor risk of colliding with a different key. However, since we're generating our schemas with code and we're not trying to construct those keys using closure syntax, instead we can build them using the keyword function, and in that case spaces actually work just fine and Datomic doesn't really care. It's a naive approach, but it lets us bring anything in and we can export it without any problems. One potential problem is that it's harder to query for statements that use these keys, but that's an unlikely case for us, so it hasn't been a concern. The only time that's actually come up is in testing, because our standards don't allow for spaces in any of our keys. Now, as I mentioned earlier, we need some way to deal with the null value in JSON, but Datomic does not include nulls or nils because not having the value has the same semantics as a value that's nil. However, it is feasible for a JSON document to care about the presence of a key even when the value isn't there, so we want to ensure that we can round trip that information. When that occurs, we use a ref type for an attribute and refer to a singleton entity with an ident of null. Now, that might conflict with the data type of the attribute in another context, but I'll show you how we deal with that shortly. Now, one aspect of attributes that's often overlooked is that they're defined using standard entities, and those entities are open, which means that we can annotate them with anything we want. In the case of arrays, we're going to need to use a structure of connected entities which means using a ref attribute. But then we want some way of knowing if the attribute is referring to a child object or to an array. So we use an internal attribute called JSON type on array attributes to indicate this. Now, the reason we need to use a structure to represent arrays is because multi-cardinality attributes have set semantics and we lose the ordering. The way we deal with that is to build a linked list using refs. The cons cells for these lists just needs an attribute to refer to the value and a ref attribute to refer to the rest. At one point, I used the previously mentioned null entity to indicate the end of the list. Since I have a strong background in RDF, and RDF includes an explicit null terminator for these lists, but that ended up being redundant and it's just annoying to deal with, so we just leave that off. Because attributes must have a data type, each cons cell needs to have a different attribute to use for each type of data that could be associated with it. That's a little annoying when we want to read from these cells, but it just requires a variable in the attribute position, which we can then bind to a set of attributes instead of referring to one specific attribute. So it's not really a big deal. One issue with linked lists when reading with the Graph API is that it requires recursion to get down the list, which can be done with a rule. But if we're using the Entity API, it provides lazy access to the entire list in one step, which can be quite useful. Finally, despite all of this effort to maintain ordering, we often use arrays because we did actually want set semantics, and the only data type that JSON provided was an array. Because of that, we've added in a contains property, which gives us a single step to every cons entry in the list. It's just a convenience, as it's just a little easier to query for that instead of using a recursive rule. So, this is an example of how an array looks. We're looking at an entity with a single attribute called data that refers to an array. The entity here is the red node. The array contains 3 values, and we can see the cons cell for each of these entries as the 3 nodes across the page, and which are then connected with the rest attribute. You can also see our contains attribute and how that connects across to the other cons cells, and that includes the reflexive one at the beginning. Note how each node is using a different attribute for the different data types, which is how this array is able to store a string, a long, and a boolean all at once. I beg your pardon? Maintaining the order of the array? Well, it's a linked list. So data refers to the first node in the list, and then that's the first element of the array. The second node of the list is the second element of the array. I beg your pardon? I'm sorry, I can't hear. The linked list contains the ordering. Okay, I'm going to move on here. So, nested objects are the other major part of structural representation. We just do that with a ref type, and that was naturally designed for nesting attributes. Well, not nesting attributes, but connecting attributes in Datomic. And just like other values, these refs can appear in arrays. In fact, for our particular use case, the predominant data type that we store in arrays are refs. Again, we distinguish these ref types using the JSON type attribute on the ref definition. Now, going back to the example on our first slide, this shows the Wilma entity at the top with its name, type, and age, and the children attribute which refers to its single entry list. And that's the cons cell in the middle. That cell then refers to its value, which is the pebbles entity, in the same way that a cons cell usually does. Being a single element list, it just refers that way. The way we've managed empty lists is when we have a reference to a cons cell that has no first value. So the schema for that, the schema specific to that data about Wilma with pebbles, is this here, which is a little too much detail for a single slide, but I wanted to demonstrate what it looked like. Of the 5 elements here, they're labelled type, first name, name, age, and children. The first 3 are strings, and age is a long, children is just of type ref, and all of them have cardinality 1, and then children has this extra attribute of JSON type array. So by iterating over our data, we can accumulate this and build that as the schema that we're going to assert before our data goes in. So this is an example of some of the JSON I worked on, lifted directly out of our systems. All of the JSON I'd been working on up to this point had been fine until I got to this specific document. I saved it for posterity, which is handy because it meant I had it to show for this talk. The issue here is that the source property, it's a bit small here, so let's look at it more carefully. As you can see, the first use is for an embedded entity, which required a ref attribute, and the second is for a string. That broke everything. It required a schema that could handle more than one data type for an attribute, which isn't how Datomic usually works. So the way we handled that was to rename attributes that we identify as having more than one type. If you can read this, I hope, then it shows a bit of pseudocode that demonstrates what we're doing. First of all, I created an ID in the let block there and used that for an entity with the label source. Then I created 2 separate attributes for source string and source object, which referred to their appropriate data types. You can see that I've said object and not ref, and that's because it allows for distinguishing between objects and arrays. Now finally, I link those attributes back to the stub entity with the original name, and that allows me to find attributes using that name. From that name I say, what are the attributes for this? And it'll also let me get from those attributes back to the original name when I'm exporting from Datomic. Now, we use a stub entity for the original name, and that's explained on the next slide, because not all of our data comes in at the same time, and our schemas may need to be built up over time. Now, attributes that didn't conflict earlier might get used for new data types in a subsequent document. So that stub entity on the previous page could actually represent an existing attribute from an earlier import. Now, that allows the attribute to continue along undisturbed in the data that was imported earlier, and new ones can take up this new pattern of how we handle duplicates. So, the general procedure we have here is that we iterate over all the entities we receive and accumulate all of the attribute names and data types they refer to. We also recurse down into arrays and objects. Once we have all of the pairs, we can then build the schema. Then we need to build the data that Naga, Now, Naga's relatively agnostic about the graph store that it uses. So rather than storing entities directly, we build the edges and assert them all in a transact operation, or transact sync. Now, building those edges uses a similar process to iterate over and into each object. And so that we can find the entities at the top of our document, Those top-level entities are each annotated with a Boolean flag indicating that they're a Naga/entity. There are a couple of ways to accumulate data as we recurse. In the past, I used a monadic approach, but that's frankly really messy. For Naga, I used a transducer, and I'm sold. We also used a protocol for the recursion, which made the dispatch on various types easy to follow and with very little code. Now, I mentioned briefly that Naga uses other databases, and we do that by wrapping access to the databases using a protocol. This was initially so that we could switch between database implementations transparently, but it has also provided some extra benefits. In particular, because queries have to go through the protocol, we can intercept them to deal with some of our schema peculiarities. It also means that we have a central place to store some of the metadata we put on attributes, and we don't need to constantly keep querying for that information. It also allows us to introduce new features such as long-running transactions which interleave reads and writes. Now, the implementation of a protocol we do through a record, and of course that's immutable. The records are immutable. Now, the record contains the connection, the attribute metadata so that we don't need to query for it again, the latest DB, and possibly the most recent transaction ID. If we perform anything that results in a new database needs a new record. Avoiding the reread of the schema metadata does need some extra bookkeeping, and that's because transact operations are usually compatible with each other regardless of state, so we can ignore the state of the connection, but updates to the schema change that. So we consider an update to the schema as being a state change for the connection and that it's pervasive across the system. So for query rewriting, because we're renaming attributes, any queries that refer to the original names aren't going to work anymore. And we handle that by rewriting any queries we get. Now that's not difficult because Datomic queries are structured data, which means that we can just iterate over each clause, descending into conjunction, disjunction and negation clauses as necessary. Now, we're not currently updating predicate clauses as we don't have a use case for that, but conceptually it's the same so long as the predicate isn't trying to do anything too fancy in external closure code that we don't have any way to see. Once the query's been executed and we've got our data back, we need to scan those results to see if any predicate values have come back in the results. And if they have, we need to rename them on the way out. Now that's particularly important when we do queries to re-export our data back to JSON. So this is an example of how we might rewrite a simple query when we're just looking for two elements that refer to the same source. It doesn't remove the case where A and B are the same, but it's just for illustrative purposes. You can see how we convert each pattern into an OR constraint with the various options. So source is converted into both source ref or source string. For those cases where the original source is also in use, we can bring that in as well. Now, a different approach is to introduce a new variable and replace all uses of the original source attribute and bind that variable to an array containing each of the attributes that the source is renamed to. And we have done that in some places, typically more in ad hoc code, particularly when it's getting, when we have the list of renamed attributes and the queries are more complex and harder to rewrite. Now, transactions have nothing to do with JSON, but the infrastructure that enables everything we've done so far also provides other features. So I think it's worth mentioning that there are benefits that go beyond the one use case of handling a particular data type. Now, anyone who saw my talk on Naga at the last conj will know that executing rules requires multiple write operations interspersed with reads. Under normal operation, that would leave the data structures in an incomplete, though not inconsistent, state during a run, which another user might see. We want to avoid that, and we do that with long-running transactions. Now, this is performed by using a speculative database through the use of with, and then replaying the data using transact or transact sync when the commit is performed. Ideally, we would use the transaction log for this replay, but speculative databases don't maintain a log, so we can't call TX range on it. Now, the way Naga manages these transactions is through the use of startTX and commitTX functions. These each return a record with a transaction started or committed respectively. StartTX just checks to see if a transaction is already underway, and if not, it records the current transaction ID and returns that new record with that ID recorded. If the transaction was already happening, then why are you calling StartTX? You might want to check your code. Now, commitTX is where the replay happens. Now, in the general case, we would need to keep our own log to replace the one that the speculative database isn't keeping. But Naga has a useful shortcut. Naga's semantics are currently for monotonic rules, which means that we only need to be concerned about assertions. We don't have to worry about retracting any data. This means that you can just query for all entity attribute values which were asserted in a transaction more recent than the last recorded transaction. If you can read it, you'll see that we also filter out datums which describe the time of a transaction, since those datums are internal for Datomic. Now, because we can't do unbounded queries in Datomic, we also attach the attribute, AX in this case, to its ident, which is information that we required anyway. And once we have that data, we find all new entities that were asserted and convert them into temp IDs for reassertion. Then we reshape the datums into an add operation and transact them all in. That's the commit operation. Now, in between the start and commit for a transaction, reads are performed as usual, but writes will use the with operation instead of transact or transact sync. The whole thing is accomplished in a tiny amount of code, like less than 20 lines. This is one of those cases where closure shows me just how much utility can be created with such a little effort, and it reminds me why I enjoy this language so much. I'm going to be wrapping up quickly, but finally, once data has been imported into Naga and processed, we need to get it back out again to send it to the systems that are interested in that data, or in any changes or if there are any changes that those systems were interested in when they had previous versions of the data. The first operation is a query to get all of those top-level entities by searching for that Naga entity attribute that we attach to each of them. And then we map the JSON reader over each of these IDs. The JSON builder over each of those IDs. That rebuilds JSON objects from raw edges. And the code could and arguably should use Datomic's Entity API for reading that data and creating JSON, but this is an example of the graph-agnostic nature of Naga, and because it gets to use the attribute rewriting code that's built into the wrapper API that I mentioned earlier. So if you're doing this for yourself with the Entity API, then you'd want to recurse into each entity, rebuilding the arrays out of lists and updating the attributes to their original names, both of which are relatively easy tasks. Everything else will already be in the correct format. Now, this was all built for Naga, as I described, I made a couple of decisions which made sense for that system, but may not be the best choice in other circumstances. So it's not a standalone library. However, most of the code is isolated into its own namespaces, so you can inspect it if you like, and a lot of it could just be wholesale lifted out of Naga. Conversion of JSON into and back from edges, or datums for Datomic, is all performed in the Naga data namespace in the Naga project. The schema generator and the API wrapper are both found in the namespaces found in the Naga storage Datomic directory. Now, if anyone wants to look into those and you have questions, then please feel free to get in touch and ask me. I work remotely from my home, and it's nice to have someone to talk to for a change. That's my contact details and the path for the GitHub project for Naga. Are there any questions? Yes.
So I see the RDF influence in the treatment of arrays. Can you prototype the alternatives?
Yes. Well, I probably didn't prototype all of the alternatives. I mentioned that I've been building up structures and arrays in Datomic in other projects in the past. One of them was where I stored a set of elements which were a bit like the cons elements, which instead of being connected with a REST attribute, they instead stored their index, and I'd rebuild it that way. That worked well. It also meant that I didn't require the contains reference to quickly get to every element in one step. And I did like that, but the code for rebuilding it was more complex. And I didn't get the natural recursive... the code for rebuilding it was much more complex, and I didn't get that natural recursion that the cons list provided for me. I think I tried another approach at one point, but they were the two which were the most convenient, and really using a linked list has proven to be the most effective for me. Well, if that's everyone, then I'm... Yes?
So, the other thing, I guess, is the presumption that conflicts are rare. Is that a presumption?
Well, sorry, what's rare?
Is it the case that you have a presumption that conflicts are rare?
They are rare. For the code that we've been working with, they have been rare. I initially wondered if perhaps I should presume that everything could have a conflict, but when I considered that, I would end up with renamed properties for everything. And while I can hide that behind the API, whenever somebody wants to go in and look at the data structure using Datomic APIs from a REPL, then they'd be encountering this all the time, and it makes for a less intuitive data analysis if you're looking at it manually. I did go back and forth on that for a little while, but one benefit to this is that because conflicts are rare, it's nice to be able to have the original name. It also means that when conflicts do come in, we often have the original name sitting there, and then we can see alternative names show up as well. It means that we've got the ability to deal with conflicts, and there don't appear to be any significant performance impacts to that. But in general, our data still looks clean and very much like the original data that was imported. Yeah.
I'm trying to reconcile in my mind the speculative transactions that you're doing.
Yes.
With that renaming, you have a long-running transaction that adds a new attribute. If you had...
Oh, okay. So when I create attributes, that must be a different transact to... So before the rule... So when rules occur, that's the only place we use these long-running transactions. The data must already be in the database. So when we do a JSON import, it requires the scan, building up the attribute definitions and transacting that. Then, once the attribute definitions are in, then we run over the data once more and build up the structure, which goes in a second transact. we're building up as much data as we can inside the graph database, and then at various times, maybe straight after a load, maybe at particular intervals, maybe on request, we're then running the rules at that point. It's only during running the rules that we need these single transact operations. It wouldn't be possible to try to squish all of the attribute definitions and the data and then the rule execution into a single transact. Okay, thank you.